matrix, as we will see. All right, so what are the basic properties that one needs to be aware of? And I'll list them and maybe show you proofs for a few of them, just to get a feeling of how things work for P matrices. They're not written in any particularly smart order here. I'll just itemize them and prove some of them, or kind of give you a sketch of the proof for some of them, or wave my hands, or wait a little bit longer until I explain why they're true. Okay, so A is real, and A is a P matrix, which, by the way, I forgot to say that I will occasionally abbreviate by writing A belongs to P. And I would like to emphasize the P, make it boldface, but sometimes I will skip that. So suppose we have such a matrix, then the transpose is, of course, P. Right? Because, that doesn't affect the transposing, doesn't affect the determinants of the principal cell matrices. Secondly, if you do any permutational similarity, so Q transpose AQ, where Q is a permutation matrix, oops, I forgot to write belongs to P. So this thing belongs to P for all permutation matrices do. Right, of course, right? Because this is essentially a similarity, right? So every principal submatrix is permuted symmetrically. So you permute the rows and the columns, and the determinants remain the same, and thus they stay positive. In particular, one other similar situation is when you do a signature similarity. So a P inverse belongs to P for all signatures. Right, that means S is diagonal matrix of plus or minus 1, and of course S is the P value. So signature similarity of P matrices, because signature similarity is not so the determinant changes predictably if a row of a matrix or a column is still by one of them. So when you perform this type of similarity, the determinant of the principal constantly changed. Easy to prove. Another property is that you can multiply from the left by D and from the right by E, and it remains a P matrix for all diagonal matrices matrices that are D and E that are invertible. So you don't want zero diagonal entries, and the product of D and E is a non-negative matrix. So typically we scale on the left by D and from the right by E using non-negative diagonal matrices, invertible diagonal matrices, and that doesn't change the fact that the matrix is P, but we can generalize it slightly. We can allow D to have a negative diagonal entry as long as E has a negative diagonal entry in the same position. So again, this follows directly from properties of determinants that are linear functions of the rows of the matrix. So this next condition is kind of a You know, so these are properties, but of course there are also characterizations, many of them. I'm mentioning them as properties, but this one is particularly useful, this fifth one, is that when you add a matrix E to the matrix A, it remains a matrix P for all non-negative diagonal matrices. If it is a zero matrix, you can have all diagonal entries positive. As long as it's a non-negative diagonal matrix, you add it to a P matrix, it remains a P matrix. And I'll mention a cute proof of this in a second. Now, this is also an interesting kind of like it. Of course, every principal submatrix is a P matrix. So it's a property that's bequeathed or inherited, if you want, by the principal submatrices. The Schur complement of a principal submatrix with respect to any of its submatrices, they're all invertible, right? So we can find these. The Schur complement is also a P matrix. We could prove this. It's essentially consequence again of properties of determinants, the defining properties of a determinant. So this is for all alpha. If you find any Schur complement, it's also a P matrix. It's essential. The principal pivot transform of every matrix, of every P matrix, is also a P matrix. And I think I'll give you a quick proof of this in a second. And there's two other things let's mention them since we are doing it. If you add or subtract F, it remains a P matrix. What is F? F is the Cayley transform of the matrix A. So, of course, we will see that every P matrix, any P matrix cannot have an eigenvalue on the negative real line. In particular, -1 cannot be an eigenvalue. So this matrix is always invertible. The Cayley transform, therefore, F, that we discussed before, is well defined. And if you add it or subtract it from the identity, you have a P matrix. And in fact, we have a nice P matrix factorization. So I'll write it here to remind you. You can write A as I plus F inverse times I minus F. So that's a factorization of a P matrix into two P matrices. Because the inverse of a P matrix, then that follows from PPT. I'll write it here parenthetically. Follows that it's a P matrix. Because if you take alpha to be all of the set 1 up to n, the PPT is the inverse. And the last property that I needed for technical reasons, let me take a matrix T and multiply by the identity, and then let me take a matrix I minus T and multiply it by A. And I'm saying this is P. What is T? I'm going to take T. Somebody's asking a question. Let me finish my sentence here and I'll see what's going on. For every T that's in the interval 0y, this is matrix interval. So in other words, T is a diagonal matrix with entries T1 down to T sub n, and all these T sub i's are in the interval 0, 1. So this here represents a convex combination of the rows of A and the rows of the identity. So if you take the matrix, create a matrix whose rows are convex combinations of the rows of the identity and the rows of A, it remains a P matrix. Did somebody have a question?
Yes, sir.
Yeah.
So in ninth you have defined I plus F and I minus F is inside P. So I have doubt like why it cannot have a eigenvalue 1. Are you considering it or I'm not getting 9?
So
Cayley transformation.
Yeah, F, this is the Cayley transform. And in order to exist, to make sense, right, I plus A must be invertible because I'm using I plus A inverse, right?
Right. Okay.
Right. Okay. And I'm saying that P matrices exist, P matrices cannot have negative numbers as eigenvalues. Okay. So maybe I'll write it here parenthetically. This makes sense because the spectrum of a P matrix intersection with the negative real line is just nothing. It's empty. Okay. So a P matrix A cannot have a negative eigenvalue, so therefore I plus A is invertible. So this F is well defined. It's called the Cayley transform. And I'm saying if you add it to the identity or subtract it from the identity, you have a P matrix. Okay? Does this answer your question? It requires proof. It's not anything you can look at it and say, oh yeah, he's right or he's wrong. These are properties that are defining properties in fact of P matrices, and some of them have substantial proofs that are needed to justify them. All right. So these are some of the basic things. Which ones? Let's pick. I want to pick number 5, and I want to pick number 8 because it's related to our discussion in this course, and prove them. This one I can prove right now. For number 8, let's just wait a little bit. There is a proof based on a corollary of number 5. Okay? So I'll try to justify. And many of them, like 1, 2, 3, and 4, don't require any proof of immediate consequences of properties of determinants. So, all right. So let's some sketches of proofs.
That seems to be another student with a query.
Yeah. Please go ahead.
Hello, sir. So, in the point number 4, can we just say that D, it is true for every diagonal matrices D and E with positive diagonal entries?
Correct. But it's a little bit more general because you can have a negative diagonal entry in D, as long as the same diagonal entry in E is also negative. Right? Because look.
Okay. So this one is the larger class.
It's a slightly larger class. I'm just being smart here. It's not really important. The main use of these diagonal scalings are, as you say, with diagonal matrices with positive diagonal entries. But we can generalize it a little bit and say, okay, the second entry of D, second diagonal entry, could be negative as long as the second diagonal entry of E is also negative. And then the determinants are still all positive. Okay? The minus. So it's a slight generalization. Okay, so let's look at A plus D. Why, when we add a diagonal matrix with non-negative diagonal entries, why does it remain a P matrix? So let's look at 5. So I'm going to take A with entries little aij, and it's a P matrix. And I'm going to take D with which is a diagonal matrix with diagonal entries D1, D2, down to Dn. Okay? And I'm going to consider A plus D. And I want to show that A plus D is a P matrix. All right, so let me prove first of all that the determinant of A plus D is positive, because that's a particular requirement, right? So let me consider the determinant of A plus D. Okay, of A. So I want to consider it as a function of that, so let me find its derivative, the derivative of this determinant with respect to the 1, 1 entry. And consider the expansion of the determinant. So actually, I'm gonna, so yeah, let me fix it. I'm gonna consider this determinant, but the way to do it, so I will find the derivative with respect to the 1, 1 entry of the determinant of A, right? So think now the expansion of the determinant of A, Laplace expansion, with, across the first row. So it's A11 times the determinant of the matrix that remains if you delete the row 1 and column 1, minus A12 times something else. None of these terms involve A11 except the very first one. So the derivative, the partial derivative, if you want, of the determinant as a function of its entries with respect to the 1, 1 entry is the principal sum matrix from 2 to n. Right? Sorry, the determinant of that. Oh, I'm so bad at doing things live, aren't I? Let me fix it. I'm writing something here that you would probably teach and explain to your first year linear algebra students, right? My goodness. That's terrible. It's okay that I'm spending time erasing here because you can actually think and know that I'm being right? So this determinant is equal to the determinant of the principal minor of A on the rows and columns from 2 to n. It comes with a positive sign, and that's the coefficient of A11 in the expansion of the determinant. But that's positive because it's a D matrix. So what does this mean? This means that determinant AA is an increasing function of A11. That's right, of the 1, 1 entry. So if you take the matrix A and you increase the A11 entry, you increase the determinant. All right, now I want to consider the determinant of A plus D. Think of it as, first of all, adding D1 to the entry A11. So add the D1 to A11 to obtain a matrix whose determinant, let me call it A sub 1, whose determinant is now positive. Because you increase the determinant by adding D1. Okay? Okay, so similarly, by expanding, okay, so let me write it this way. Similarly, this applies to every principal submatrix of A1, okay, they have positive determinants. Right, because okay, a principal submatrix of this new matrix A1 is either a principal submatrix of A with no changes and therefore it's still positive, or it's a principal submatrix of A that contains the A11 entry, which had positive determinant. Its derivative with respect to A11 for the same reason is positive, so it also increased. So in other words, I'm telling you, this is a sketch. A1 is P, is a P matrix. So if I increase the 1-1 diagonal entry, I obtain a new matrix that's still a P matrix. Well, similarly for A1 with P2 added to its 2-2 entry, which is A22. Okay, you will its derivative, the derivative of the submatrix of A1 and of every principal submatrix that contains that row is positive because the original matrix is A, and A1 is still a P matrix, and therefore all these determinants are going to increase. So to obtain submatrix A2, we have A2 is a P matrix. So one by one, if you want, add the diagonal entries of D to the original matrix A, and you keep the outcome a P matrix. So in the end, A plus D is a P matrix. Okay? I mean, this requires a lot of the technical details that I'm skipping, but I want you to just get the idea. Right? Adding a diagonal matrix, a negative diagonal matrix, you can think of this doing it one entry at a time, and all you do is you increase or leave the same, if that diagonal entry was 0, the principal minors. Therefore, you retain, simply because the derivatives with respect to the diagonal entries are principal minors, which are positive. Okay? So, right in the expansion of the determinant with respect to any row of the matrix, the term that comes with the diagonal entries always comes with a plus sign. So its derivative with respect to the entry, it's always plus, the positive version of the principal minor that remains. You delete that row and that column, and they're all positive. So that gives you that adding a diagonal matrix doesn't affect the fact that it makes it even more P if you want. So it can only increase the determinants of the principal minors. Now, I wanted to present you a proof also of the PPT. We can do a direct proof. In fact, in the notes that I will distribute to you, there is a direct proof. Here's the PPT, here's its basic factorization, blah, blah, blah. You find that the determinants of all the principal minors are positive. But I want to present kind of like a more practical explanation as to why the PPT is also a P matrix. And for that, I will use, so I'll stop here and I'll go to another basic result, basic characterization of a P matrix. Okay, that will help us prove will help us prove what was it? 8. That the PPT is of a P matrix is a P matrix. This basic characterization of a P matrix. It's the most effective one when you work with P matrices, in my opinion. Not that it's easy to check because it involves every real vector, but it's something that kind of like gives you a geometric, if you want, idea as to what P matrices are. So A is a P matrix. This is real, for only for real P matrices. A is a P matrix if and only if for every vector x in Rn, except the zero vector, there exists an I, an index I, such that x sub I, the ith entry of x and the ith entry of ax have the same sign, so they're positive. This product is positive. So, in other words, P matrices, as we say, cannot reverse the sign of a real vector, real non-zero vector. In what sense? Take every positive entry and turn it into a negative or zero. Take every negative entry and turn it into a positive or zero. There's got to exist, if it's a P matrix, you give me an x that's non-zero, there's got to exist an entry of x that's non-zero, and the corresponding entry of A times x has the same sign. Okay? It's a characterization. The proof of this, essentially, just a sketch of the proof of this, is that if xi times, for some vector, if this is less than or equal to 0 for all I, okay, then there exists, then you can construct D, that's a positive diagonal matrix, D greater or equal than 0, a diagonal matrix such that A plus D is non-invertible, which violates the thing we just proved, which was, what number was it? 5. Because we proved that if you have a P matrix and you add such a matrix D, you get a P matrix, which is necessarily invertible. So you can, using this contrapositive, if you want, in fact, you can go both ways. You can prove that a P matrix is exactly a real P matrix, exactly a matrix that doesn't reverse the signs of non-zero vectors. Okay. So a P matrix A, it's an informal sentence, but just to get the idea, does not reverse the sign of a non-zero vector. And by reversal, I mean changing a positive to a negative or 0, or a negative to a positive or 0 of any non-zero vector. So that's an effective characterization of P matrices. That's a consequence of the proof that we gave of 5, right? I mean, that's really what's behind it. Some people actually define P matrices like that. It's rare, but because it's a lot easier to just say all the principal minors are positive, but this is an effective characterization. Now, we can use it to prove that the principal pivot transforms of P matrices are P matrices. So let me do that. So I think I'm going to take more time, a little bit for this first hour, completely, I guess, to do P matrices. Now I'm going to take a little bit of time the second lecture on semi-monotonicity. So now we can prove PPT of A alpha is also P. Okay, I don't have it written in front of me, but let me try to explain it. So let me put proof in quotes. Okay, so it's enough to do PPT, to prove this for PPT for alpha being just well, 1, 1, right? Well, because first of all, that PPT exists. The A11 entry of A is positive, and therefore it's invertible. Secondly, we've learned when we discussed PPTs that any PPT can be thought as a sequence of PPTs of singletons, which represent a partition of the set alpha that you may have. Okay, so if we do it for one, we can do it for the second, we can do it for the third, for any of the diagonal entries of the principal submatrix residing in the alpha position. So it's enough to just do it for one. So let's say B is the PPT of A with respect to the 1, 1 entry. So I have A multiplies the vector x1, x2 down to xn, and gives me a vector y1, y2 down to yn. And that's equivalent to saying that B multiplies the vector y1, x2 down to xn, and gives me the vector x1, y2 down to yn. Okay? So take now a random vector x, that's non-zero. Since say it's a P matrix, it means there exists an I such that xi times yi is positive. Okay? but I mean, you have the same pairs of vectors here. That also means that one of the edges. So it also means that xi times yi is positive on this side too. Even if I is 1, you have y1 x1 and x1 y1 are the same. So B cannot reverse the sign. Of any vector of the form of y1 x2 down to xn. That's different than 0. Right? Because if it reversed, if every entry here, y1 times x1, x2 times y2, xn, yn, was less than or equal to 0, that would mean that A had reversed the vector x. And that would be a contradiction to the matrix B. So for that very simple reason, PPTs, it's because of this, the mapping property with respect to 1, and therefore with respect to a lot of. So this, B remains a P matrix, so all its diagonal entries are positive, so you can keep doing PPTs of it as much as in any way you like. So collectively, you perform all the entries or elements of alpha, and you obtain a PPT matrix. So that proves 9 in our main first theorem. But I want you to retain also this basic characterization. Okay. Again, in the notes that I will distribute, there is rigorous and complete proofs, sometimes different from the sketches that I'm giving here. Another now very essential, very esoteric, very, very descriptive characterization of P matrices. of real P matrices. But I think will bring us back to very basic things we know. So a real matrix P, A, sorry, a real matrix A is a P matrix if and only if you take any principal submatrix of it, so if you choose an alpha, a subset of 1 up to n, the spectrum of the principal submatrix A of alpha that's real, so all the real eigenvalues of every principal submatrix are positive. Okay, all real eigenvalues of every principal submatrix are positive. So it doesn't matter what happens to the complex eigenvalues, the non-real eigenvalues. The real ones are positive. That's a good enough condition to imply that a matrix is a P matrix, and of course it is a necessary condition for every P matrix. So proof, sketch of proof. Okay, let's look at A. So the determinant of A is the product of the eigenvalues. So if this condition holds, right, it's the product of the real eigenvalues, or product of the complex of the non-real times the product of the real eigenvalues, right? The non-real eigenvalues come in conjugate pairs. I don't know why this quit. Why are you doing this to me? The non-real eigenvalues come in conjugate pairs. So this product here is positive, right? First of all, they're non-zero, right? So I'm assuming that A is in that A satisfies this condition. A satisfies condition. So on the right. So zero would be a real eigenvalue, and therefore it cannot be an eigenvalue, because it would have to be positive. So the product of the eigenvalues, which is the determinant, the product of the real times the real. The real eigenvalues are positive, so the determinant of A is positive. Now apply this to every principal submatrix, because that's my assumption, that every principal submatrix has this condition. Okay? So if you have a matrix for which every principal submatrix, its real eigenvalues are positive, necessarily it's a P matrix, because the determinants of all the principal submatrices have to be positive. Okay? Conversely, if you have a P matrix, right? So if A is in P, the real eigenvalues must be positive. I hope you see why, right? Because AX equals lambda X, and lambda is real. If lambda is less than 0, then A reverses X, the sign of X. Because you have A times X equals a negative multiple of X. that would be contradiction. Contradiction to A being in P. Right? Because it would reverse the sign of the eigenvector. Same applies to all the principal submatrices, because if A is in P, all the principal submatrices are in P. So therefore, none of the principal submatrices has a negative eigenvalue. In other words, the condition on the right holds. So, in other words, this is a nice way of thinking about P matrices. The real eigenvalues of the matrix and all of its principal submatrix are necessarily positive numbers. Okay? Not that it's easy to check, but it's effective in certain discussions. Okay. I'll just spend another 2 or 3 minutes on this, and then we'll take a little break. Another important aspect that we have already discussed, and I'll stop with that for now and have a little break, is that, of course, A being a P matrix implies that A is semi-positive. I admit it took me a while in my career and work with P matrices to realize that. Okay, I did not know this for a long time. So in other words, if you have a P matrix, then A maps a positive vector to a positive vector, right? Because this means there exists a non-negative x such that AX is positive. The proof of this is based on a theorem of the alternative, okay, which is a theorem in inequality theory. So it's a theorem in inequality theory. I don't have time to singly mention it, but in general, if you prove the contrapositive, if A is not in SP, so for every non-negative x, A times x is not positive, that means that there exists an x that's non-negative. There exists an x that's non-negative such that A transpose x is less than or equal than 0. That's a theorem. It has a name, but I don't remember it now.
Steenke's theorem.
Okay, very good. All right, so there exists, so if A is not, it violates the definition of semi-positivity. It means A transpose reverses the sign of a non-negative non-zero vector. Okay? And that therefore implies that A transpose is not in P, right? But that implies that A is not in P, right? Because when you transpose a P matrix, you get obviously a P matrix. So therefore, not in P, and not in P. So therefore, not in SP implies not in P. Therefore, P implies that it's semi-positive. So that's kind of a. I'm being a pure-minded matrix theorist. I would like to kind of like think of a way to prove this directly without using a theorem of the alternative. But so such is life. But sometimes we need stuff we don't like. Not like, but not fully understand. And of course, I mentioned before another fact that A is a P matrix if and only if SAS is SP for all signatures. signatures S. So there is a stronger connection between P and semi-positivity. You gotta enforce semi-positivity for all signature similarities. Now this theorem I discovered kind of like accidentally myself, but of course it was known. It was proven in a short paper in an algebra journal. I don't understand how it ended up in an algebra journal, whatever, 30 years before I realized it is true. It's not, again, it's a theoretical use, because you can't possibly, semi-positivity you can check in polynomial time, but then of course you would have to check an exponential number of matrices that is semi-positive. So it's not a practical characterization, but if you think about in terms of reversal of sign, it says that a matrix is P if and only if it's semi-positive with respect to every orthant, right? So there exists an X in every orthant, such that A times X is in the interior of that orthant. That's what it really says. I'm talking about the quadrants or octants or whatever of Rn. All right, I'll take a little break here. I have another 10-15 minutes worth of P matrices to talk to you about, and then I'll move to semi-monotone matrices, which are a natural generalization of P matrices. P matrices are semi-monotone. I'm open to any questions you have now or after. Let's take a small break. Anideepa will set the rules when we come back.
No, after 10 minutes or 15 minutes, maybe we can come back after 10 minutes. Is that okay?
Yeah, 10 minutes is fine. Yeah.
Okay, then maybe we'll be back at 9:15.
Okay.
We'll be back at 9:15 maybe.
Okay.
So we'll take the questions maybe later on.
Take the what?
No, I think someone has questions, so maybe we can take the question after the break.
Yeah, excellent. Yes. Okay.
No, this line connection is working. Hmm.
All right, I am back. Um, are there any questions? Please ask them if you have a question.
Yeah, Shonali, are you there? I think she was having some question.
Yes, ma'am.
Yeah,
I
you
want
please-
to ask. So, does there exist any characterization for 2 cross 2p matrix or 3 cross 3p matrix? How do they look like?
Tell me again, what type of P matrix? P matrix?
Any characterization for 2 cross 2p matrices
Oh,
or
small P matrices. Well, none that's different than the equivalent conditions we mentioned, except for 2 by 2 and 3 by 3, the conditions are easy to check, right? I mean, there's either it's for 2 by 2s, it's just that if the determinant is positive and the diagonal entries are positive, then it's a P matrix. And a very confined set of conditions for 3 by 3s, because you have the 3 2 by 2 determinants, the 3 by 3 determinant, and the diagonal entries. So there's a otherwise the sign pattern, except for the diagonal entries being positive, is not, which entries are negative and which entries are positive, is only what makes the determinant being positive. So there are some special cases where you can look at a 2 by 2 and a 3 by 3 and say, oh yeah, obviously it's a P matrix. But generally, it's not a very generalizable type of condition. Of course, upper triangular matrices with positive diagonal entries are P matrices, whether they're, regardless of the size. So there are some, quick answers if you have a positive semi-definite, a positive definite matrix, and so on. So yeah, I wouldn't call looking at a 2x2 or a 3x3 matrix and deciding that it's a P matrix or not a very practical approach to the problem. Yeah. So I don't know. Look, in fact, I am lying to you. There is something that we will learn perhaps tomorrow. Yeah, tomorrow that will maybe give more insight as to what small P matrices look like. Okay, but in general, think about the few conditions that are imposed by the determinant, the principal numbers, having to be positive. If it's a small matrix, they're very controllable. I hope I answered your question. But it's a good thing for any one of you to practice that. Take a 2x2 and kind of try to think what needs to happen for this to be a 2x2 matrix. Is very straightforward. Yeah.
I'm just curious about one thing. The P matrices are defined for square matrices, because we're
Right.
considering all the. So if we see this that P matrix, if and only if it doesn't reverse the sign of an non-zero vector. So if that can be considered to generalize, can it be generalized for a non-square matrix also?
Yes.
Is there any?
Right. I mean, there are generalizations of the notion of P matrix that are not based on its definition as a condition on the principal minors, and therefore they're applicable to even rectangular matrices. Yes, and that's why I said some people prefer to define the notion through the reversal of sign, because it lends itself to this type of generalizations. There are generalizations in many different directions and ways. We can talk about functionals that have P properties. You can talk about block P matrices. There's all kinds of generalizations of the notion. Yeah.
And those generalizations, does that have any relations with the LCP? Any kind of people are trying to do?
Yeah, not that I know of. Yeah.
Okay.
I mean, unless you're talking about generalizations of the LCP.
Mm-hmm.
Yeah.
Okay. Yeah.
Yeah. I mean, my general idea is when somebody can generalize. I mean, it's the very first thing that we all naturally think of. How can we generalize? And the P matrices have been around for a long time, so they have been generalized in many different ways. One way is what you just mentioned. Yeah. So define a reversal. Another way is a property that to generalize P matrices is a property that I'll mention now very quickly. So a few more things. I will cut that short because most of the things I have more to say about P matrices will fit nicer in the session of open problems, because there's tons of open problems on P matrices. Notoriously hard. So here's another property that lends itself to generalization to rectangular matrices, but I won't go into that. Another fact, when you have a matrix A and you have factored it as the product of two matrices, B and C inverse, Here, we're going to take this to be in Mn, and these also to be in Mn, both of them. Okay. But you can, to be M by N, and A therefore would be M by N, but have the inverse. By the way, this particular result that I mentioned has been generalized to even C being rectangular and replacing the inverse by some version of a generalized inverse there. So it says this fact says that this is a P matrix. So a factored matrix of this type is a P matrix if and only if you take the two factors and you find the matrices whose rows are convex combinations of the rows of B and C. So in other words, if you look at all the matrices T times B plus I minus T times C, this is invertible. For all T that are in the matrix interval 0 identity. So if you take T to be a diagonal matrix whose diagonal entries live between 0 and 1, and you form the matrix T times B and I minus T times C, you get an invertible matrix, or a full rank matrix if you go into rectangular generalizations. So this is convenient because many times we can factor matrices, and if you can factor a matrix, in some sense, you have now a way of checking of whether it's P based on.
This B is not necessarily to be invertible, no? That B matrix only is. So then can this T can be I?
The BI, yeah. If you take it to BI.
So if we'll take, because T is belongs to 0 I, so that's.
Yeah. So here it's not invertible, right? Well, I don't say it's invertible, but A being the product of B and C inverse, A having to be invertible forces B to be invertible. Right? If all the matrices are square and A is a P matrix, P matrices are invertible, their determinant is positive, so therefore B is invertible. So forget this. If you say A is equal to BC inverse, and it's a P matrix, that forces B to be invertible, even though it's not said. Agree?
Yes.
Yeah. I'm sticking now to the square case. If you want to generalize this to rectangular matrices, then the story is different. Yeah, you're right now. On the right-hand side, this is also imposed as a condition, right? Because as you say, if you choose T to be the identity, then we only have B, and it says B is invertible. So B is invertible, C is invertible, all the convex combinations of the rows of B and C in terms of rows, because when you multiply from the left with the diagonal matrix, you're scaling the rows. All these matrices are invertible, and that's equivalent to B times C inverse being a P matrix. So this generalizes another simple fact. When you have A equals BC inverse has no negative eigenvalue, if and only if T times B, little t, plus 1 minus T times C is invertible. For all little t in the interval 0, 1. Right? I mean, this is easy to prove. It's in fact in Foreman Johnson's book. So when does the product B times C inverse has a negative eigenvalue, it forces the ability to choose the little p here so that this convex combination of the matrices B and C are singular. Is a singular matrix. So this generalizes something that's true in the scalar case into P matrices. So anyway, this has been also used, if I recall correctly, to provide a generalization of the notion of P matrices, okay? By looking at this and replacing it by B and C being rectangular and forcing this convex combination to have full rank. Okay, so that's another way P matrices have been generalized. So this condition has lent itself to a generalization, and then it implies something involving generalized inverses. Okay, so a final thing that I want to talk about, which is actually a little bit related now to this, is that talk a little bit about the spectrum, because for every class we discussed, we also examined this. What are the eigenvalues? Okay, so there's a well-known result, and they say that so if A is a P matrix, in fact, so we'll take it to be real. In fact, this is true about complex P matrices as well. Then here's what I'm going to do. I'm going to draw the complex plane here, and I'm going to draw a sector on the left, which I'll shade. Okay. All right. So what is this sector? I'm going to switch colors here because my pen died. Okay. So here is the angle pi minus pi over n. N is the size of a matrix, and this is pi plus pi over n. Okay, and this is a closed sector there. So let's call this one K for Kellogg. Okay, it turns out that the spectrum of A does not intersect this sector K. Okay, so every P matrix cannot have an eigenvalue in this sector. So K for Kellogg, who first proved this result. Now, but they can have all its eigenvalues except at least one. For example, on the real positive line, because remember the trace has to be positive, so it's got to have an eigenvalue on the right half plane. But all the other eigenvalues could be in the left half plane, but they would leave outside this region K. Okay. In fact, there is a little bit of misunderstanding, or not misunderstanding, but there's a hidden issue here with respect to this. This is a property that's not, it's a consequence of being a P matrix, but there are more matrices that satisfy this. So let me write this down. In fact, the spectrum of A intersect K is empty for all A whose sums of I don't know, I used K already, for all M by M principal minors for M equals 1, 2, up to N are positive. So we don't need to have all the principal minors being positive, but we want the sum of all 1 by 1 principal minors, the trace. The sum of all 2 by 2 principal minors. The sum of all 5 by 5 principal minors to be positive. If you have such a matrix A, then its eigenvalues cannot be in that Kellogg, in that region K, right? So we in matrix theoretic literature, this class has a name, and unfortunately they call it Q. So I'll say here we say A belongs to Q, but not to confuse it with the Q that means the LCP has a solution. I'll call it Q hat. Okay, and I will come back to this because I'm interested in the relation of Q as it appears in LCP with this Q hat. Okay, so what happens is that the eigenvalues not being able to be in this region is a consequence of the characteristic polynomial having alternating coefficients, right? The trace is positive, so we have the leading coefficient is 1 is positive, minus the trace is negative, plus the sum of the 2 by 2 principal minors, minus the sum of the 3 by 3 principal minors. All of these for P matrices are positive, all these sums. So the characteristic polynomial has alternating coefficients of a P matrix. And that forces the eigenvalues to be outside this region K. But it's true for every matrix in this class. Right? And that leads to a plethora of interesting questions regarding the spectra of P matrices and Q hat matrices. And I will come back to them on our last day. Okay, so enough about P matrices. You'll have a lot more to read if you're interested when I circulate notes, but I think the idea is now here to get a little bit of the flavor. I'll talk now a little bit about another class that's of interest. I can find my notes. Here they are. I'm going to talk about semi-monotone matrices. I'm not going to talk about central matrices today. I think we have enough semi-monotone matrices. We've discussed them. It's the class E that we put in a tree of classes on yesterday. Okay, semi-monotone. All right. What are they? Let me define them. And they are kind of like one more abstraction, kind of like a generalization term beyond P matrices. So they remember in our relation hierarchical scheme, they were in between the P matrices and the semi-positive matrices. Talked about semi-positive, we talked about P, now we look at what's in between them. Okay, and they're the semi-monotone matrices. And they do play a significant role in the LCP, very much like the semi-positive and the P matrices. Okay, so again, we're going to stick with real matrices. So A is an n by n square real matrix. So is I'm going to say semi-monotone, and we're going to write A belongs to E sub 0. we define them as strictly semi-monotone. So this is the semi-monotone, E sub 0. If for every non-zero x that's greater or equal than 0, there exists a k in the set 1, 2 down to n, such that xk is positive and a times xk is positive. So, in other words, when it hits a non-negative non-zero vector, it retains the sign of a positive entry. Right? There's a positive entry on the x that gets mapped to a positive entry on the right. Yes, you have, Bharat, you have a question?
Yes, sir. Sir, it should be AXK is non-negative or positive? Kth coordinate of AX.
Oh yeah, I'm defining the weak version. So yeah, you're right. Let's make it non-negative.
And I have another question, like why we are calling it as a semi-monotone? I just want to know.
Tell me again.
Why we are calling this type of matrix as semi-monotone? What is the reason?
Oh, right. Yeah, that's a good question. And I remember we had a hard time explaining monotonicity. Remember, monotonicity implied that if implied that if AX is greater or equal than 0, then X is greater or equal than 0, right? But that was for all X's, right? So for all X's for which A times X is greater or equal than 0, then X was greater or equal than 0. Here, in some sense, we have a weaker version of that because for this type of matrix, it doesn't have to be for all X's for which AX is greater or equal than 0, X was positive, is greater or equal than 0. So I mean, it's a weaker version. You can think of it as a weaker version of monotonicity. I don't know exactly. I mean, this is a mystery here. Why people name things, I don't know. How do they name them? They don't always make sense, right? It's a weaker version of monotonicity. Go back and see what monotone meant, and you'll see that kind of it's like a weakening of that notion. So, I'm not completely. Don't hold me responsible for all these names. And we're going to call it strictly semi-monotone, right? So this is the notion we discussed, and we'll say A is in E if for every X different than 0, greater or equal than 0, there exists a K and 1, 2 down to N, such that X of K is positive and AX of K is positive. So I mean, this allows, semi-monotonicity allows for a matrix to have a non-negative non-zero vector as a null vector. Strict monotonicity requires that it takes a positive entry to a positive entry for all such vectors X. Okay, so lots of facts about this. I mean, a graduate student of mine a few years ago, was looking for a problem, and we decided, I didn't know about this class at all, to be honest. And we decided that's interesting. It kind of generalizes. In some sense, it says you cannot reverse non-negative, non-zero vectors. Cannot reverse the sign, right? Mostly a generalization of P matrices in terms of the reversal of sign. That's what it says. So that's why it contains the P matrices, right? And there's also this notion of P0 matrices, which we didn't mention, that allows for minus to be 0. But we don't need to go to that right now. So, and the first question that came to my mind, all right, so what do they look like? I mean, you asked earlier, was it Somali that asked, what do 2 by 2 and 3 by 3 P matrices look like? I asked the same question, what do 2 by 2 and 3 by 3 semi-monotone matrices look like? And I think we answered that, but it's not a pretty answer. Generally, we don't know. Okay, there are some characterizations that are mentioned that I will mention, but they don't lend themselves to looking at the matrix and quickly deciding whether it's semi-monotone or not. Okay. So let's cover some basic facts, and this will become apparent. So this is a class of matrices for which there's lots of room, for new ideas and research. So I will try to stick to the strictly semi-monotone matrices. For everything I say, I think that I'm sure there is a version for the semi-monotone. But let's stick with E. Okay? Let's stick with E in the interest of finishing today. So A being a strictly semi-monotone matrix is equivalent to two things happening at the same time. First of all, every proper principal submatrix is in E. Okay, so every proper principal submatrix belongs to E. By proper, I mean everything except the whole matrix. So really what it means if you go from left to right, it means that if A is in E, then every principal submatrix is in E. Right? To go backwards, you don't need only every proper, but you need a second condition, and the second condition is for every positive x, for every x that has positive entries, there exists a k from 1 up to n, such that AXK is positive. So it's a subtle difference. It's a subtle difference, or it's a slight relaxation of the definition of strictly monotonicity to go from right to left. Right? Because in the definition of strict monotonicity, you wanted this to happen for all non-negative non-zero vectors. But you can relax this a little bit. I want only for the positive vectors to have a positive entry in A times X. If you combine this with every proper principal submatrix being strictly semi-monotone, then that forces the whole matrix. It's a little revealing, but also revealing of the difficulty in characterizing semi-monotone matrices. Because strictly semi-monotone matrices, because we cannot possibly check the defining property. We can't work with all non-negative x's. But at the same time, even if you force the x to be positive, it's still not enough. Or even if you knew for some reason that every proper principal minor was strictly semi-monotone, it's not enough. So there is some inheritance, but it doesn't help very much. It's kind of like a recursive inheritance. It's not easy to apply. So when I saw this, and this was a known result, we didn't invent this. it was in the literature. When I saw this, I realized questions about strictly semi-monotone matrices are non-trivial. Okay? If that's the best that's known about them. And particularly, this implies that the diagonal entries are positive, right? Of a strictly semi-monotone matrix. But the rest of the signs of the entries are not set. So another fact that's kind of very closely related to this is that A is a strictly semi-monotone matrix if and only if the proofs are not, proofs of these equivalences are not, they're not hard, but they're technical. Okay, they're not conceptually hard, but they're technical. So another nice property is that A and all proper principal minors, principal submatrices, so everything, including A itself, are semi-positive. This looked a little bit more promising, and I think it's a little bit more. It fits in my brain at least a little better, because semi-positivity is something that I semi-understand. So this says that semi-monotone matrices leave inside the semi-positive matrices, but in fact, they require all the principal submatrices to also be semi-positive. Again, that's not something that it's easy to check. But this one lends itself more to special classes, right? Because, for example, very quickly, P matrices, therefore, because of this fact, are strictly semi-positive, semi-monotone, right? Okay, we can go through the definition, but every P matrix is SP. We proved that. Every proper principal submatrix of a P matrix is a P matrix, so they're all SP, and therefore the matrix is strictly semi-monotone. A mouthful, but it's interesting. And another fact that connects it with our main object. So A is strictly semi-monotone if and only if the linear complementarity problem, and that's the association with our main object here, has a unique solution for all positive Q. Okay? So I didn't mention it for P matrix because we had mentioned it before. A is in P if and only if the LCP of QA has a unique solution for all Q, whether it's positive or not. Semi-monotonicity, strict semi-monotonicity is associated with uniqueness of solution of the linear complementarity problem for positive vectors Q. I want to ask the same questions now. What are special classes that look like that are semi-monotone, strictly semi-monotone? What about their eigenvalues? How about characterizing them or constructing them? Okay? So I'll quickly go through some of these ideas without very many details. And again, in the notes I will provide you all details that are in there. Some basic classes. Okay, look at hierarchy. I won't write them again. Remember, we had a nice hierarchy, and the first line said all kinds of non-negative type matrices were P matrices, and therefore they were strictly semi-monotone matrices. So lots of classes, the P matrices, the M matrices, the positive semi-definite, the positive definite matrices, lots of them are strictly semi-monotone. So I can get away with just saying, look back at our hierarchy. So another, yeah. Okay, another interesting, yeah, go ahead.
Sir, here you are representing strictly semi-monotone by E or semi-monotone by E?
I'm talking about E, but you can extend these to E0. So in hierarchy 3, we had E, right?
In the last fact, you said LCP comma A has a unique solution for all Q positive.
Right. Yeah. Right. This is for.
So it should strictly semi-monotone.
What is your question? I don't understand.
I'm asking if A is strictly semi-monotone, then LCP has a unique solution for all Q positive.
Right. That's a fact. Yeah.
Okay, but I think it should be for non-negative.
Non-negative Q?
Yes, please.
You could be
for
right.
strictly semi-monotone.
You're right. You're absolutely right.
Yeah.
Yes. That's for all Q non-negatives. You're right. Thank you. In fact, if A was in E0, then it would have to be. Yes, you're right. It's kind of like a little counterintuitive. So let me write both. Thank you. So if it has a unique solution for all positive Qs, it's an E0. If it has also a unique solution for Q equals the 0 vector, then it's in E. Thank you. Yeah, thank you. All right, so if I take A in E, I'm translating everything from E0 to E. So I'm bound to introduce some errors here. So if I take a matrix A in E and I take a matrix B greater or equal than 0, then A plus B is in E. Okay? I think that's easy to prove. And that would be for E0 as well. True. Of course, permutational similarities are true as well. A in E, P permutation matrix. Then P times A, P transpose is also in E. So it's preserved under permutations. It's preserved under diagonal scaling. So I'll say A is in E, D is invertible, D variable is an invertible, I'll take an invertible diagonal matrix. That implies that A times D and D times A are also in E. So you can scale either the rows or the columns by positive numbers and it remains strictly semi-monotone. The converse is not true. up here the converse is true. This I don't really want to state the converse yet, but I will say, so let me put it here parenthetically, converse of last implication is not true for E0, okay? We struggled to find a counterexample. So in other words, find something where A times D, for example, is in E0, but the matrix A is not in E0. So let me write it down because it's illuminating. Let's take A to be the matrix 1 minus 2 minus 2, 1. So it's even symmetric. And let's take D to be the matrix. Now it doesn't have to be invertible, so I'm going to take the matrix 0, 0, 0, 1. Okay, so verify that A is not in E0, but which one? But AD is okay. I mean, if you try to force for a non-negative non-zero vector x, A times x to have a positive entry, it doesn't, it never works. But if you multiply, if you scale the columns by this D, because you kill the first column, then the matrix is in E0. So it's really hard to find even small examples to illustrate the various scenarios that can arise with semi-monotonicity. Another simple fact, every companion matrix will answer another question of interest to me. Every companion matrix, what is a companion matrix? 0, 0, the companion matrix to a characteristic polynomial, right? A polynomial. Minus a 0, 1, 0 of zeros minus a 1, 0, 1, 0, then all zeros minus a 2, and so on. The last row is 0, 0, 0, 1, and then minus a sub n minus 1. So if you take a matrix of this type, this is like a companion matrix of a characteristic polynomial, belongs to E0. It's easy to prove that. Since, I don't know what should I call this, C, so since determinant, the characteristic polynomial of C is an arbitrary polynomial, right? I'll have a 0 down to a and minus 1 being real numbers, any real numbers you want. We have that semi-monotone matrices can have any real spectrum, any spectrum of a real matrix. So there's no restrictions. And we know, yesterday when I made the mistake and I said the same thing about semi-positivity, I forgot the negative multiple of the identity that's not allowed. I had this one in mind. I had just read this one last and I said, oh, everything is. So truly everything for for semi-monotone matrices. Yeah, and so that there's no imposition on the spectrum if you go to E0. Now, it turns out that A belongs to E0 if and only if A plus epsilon I belongs to E for all epsilon greater or equal for all epsilon 0. Okay, so you can kind of like translate here. So in other words, every spectrum of an invertible matrix, so it doesn't have to be that. Any spectrum again can be achieved by a semi-monotone matrix, right? You just have to translate it by an epsilon. So we can state that result for strictly semi-monotone matrices. So here comes now the biggest. Here's a question.
Hello, sir.
Yeah.
So this companion matrix is in E naught. It is a semi-monotone. So, sir, for semi-monotone, we have okay, diagonal entries has to be non-negative.
Right.
So this an minus 1. The last entry in the companion matrix is minus of an minus 1.
Yeah.
So that will reduce an minus 1 to be less than equal to 0. I'm just not able to understand this that semi-monotone matrices can have any spectrum of a real matrix.
Right.
Can you please explain it?
Yeah. Let me think a little bit about it. You're right. We've imposed a condition here, right? So that an minus 1 is less than or equal to 0, right? I'm listening to somebody who's smarter than me. Yeah. I'm trying to think if that's really an imposition or we can, negate everything. So is it true so AA minus 1 is the trace, right? Yeah. Let me think about this. I think there is a trick that allows to play with the sign of one of the coefficients of a polynomial.
Sir, an minus 1 should be the trace, and trace is non-negative, I think, of this matrix.
Right. So an minus 1 is the trace here.
Negative of an minus 1 is the trace of M.
Right. So so the question really is, because you can choose the trace to be 0, right? But the question is, does this is this matrix in E0? Because if it is in E0, an minus 1 cannot be a positive number, right? So in other words, this formulation does not allow for a particular trace. So there may be a condition that I'm missing, and I copied it wrong on the trace.
So trace has to be non-negative here.
Right. The trace has to be non-negative. So So, okay, so we can add this tentatively, but I'll investigate it here. So since there's an arbitrary polynomial, we have that someone can have any spectrum of a real matrix with non-negative trace. Oh, I was wrong again. but let me investigate it, right? Let me see if I made some error in what I copied. You're probably right. It needs no negative trace. Yep. All right. So, sounds good. You guys are really, really good. Thank you for fixing all my mistakes. All right. Let me mention one last result, and I think I will stop with that here. Oh my goodness. I think I should show it to you. Look at my notes. For every sigma with a positive trace. So yes, we fixed it. Thank you. I can't even read my notes. All right. So here's, I'll mention to you now an intriguing problem. And that will be my last point of discussion here. If A is a P matrix, right? Then of course A is strictly semi-monotone. If B is a non-negative matrix, or if you want entry-wise positive, whatever you want, then of course B is in E0, for example. If you make it positive, is in E. As a consequence of these two things, A plus B, right, because the sum of two semi-monotone or strictly semi-monotone matrices, here it's one of them is strictly, then this is in E. Anybody has a disagreement? If you add two semi-monotone to strictly semi-monotone and semi-monotone matrix, the definition of strict semi-monotonicity is still there. The X that works for A works for A plus B. But these are entry-wise non-negative. So conjecture, all matrices in E are of this form. In other words, P matrix plus non-negative matrix. So I do not know the answer to this, so the only thing I know is that we failed to prove it, and we failed to find the counterexample. The effort to prove it will point you as to why might there be a counterexample, but it doesn't quite let you find one. So I'm leaving this to you as your biggest challenge, and see if you can come up with a resolution of this at some point. So this conjecture is not totally out of the blue. Okay, so this is related. This conjecture is related to copositivity. Let's say strict copositivity. remember this is the CP class. Remember that said that X transpose AX is positive for all X greater or equal than 0 and different than 0. We call such a matrix co-positive. And there was a conjecture for a long time conjecture. I don't know if any of you have seen this, was that CP is actually positive definite plus non-negative. So all you needed to do is prove that a matrix is the sum of a non-negative matrix and a positive definite matrix, and that made it doubly entry-wise EN or EP entry-wise positive, and that would be enough to show that it's co-positive. Of course, it is, but also the other way around, that every co-positive matrix was the sum of a positive definite and a negative one. But after a few decades of this being a conjecture, well, this was disproven by Horn. This is not Roger Horn, it's another Horn. There was a counterexample. It's a fairly large matrix. It's not a small 2x2, 3x3. I forget the size now. It has to do with projective planes, but it's co-positive, but it's not the sum of a positive definite. Actually, I think we called it just C, not CP. CP was the completely positive, so this is C. So it was proven that a matrix is co-positive, strictly co-positive, but it's not the sum of a non-negative and a positive definite. It cannot be written as such a sum. So it is possible that, this is a different type of problem, but it has the same nature, the same feel. But it's possible that this conjecture is not true, but we cannot find a counterexample, and we cannot prove it either. That strictly semi-monotone matrices are P plus non-negative. Any questions? I think I've lost control of the time I've taken a lot more time than I was supposed to. I apologize for that. But that's all I have for you for today.
Thank you, Michael. So, anyone has any questions or any doubt, any comments? I guess they already asked their.
They're working on the conjecture. Yeah. Very good. Thank you all, and I apologize for. Yeah.
Thank you.
All right. Thank you very much. I'll see you tomorrow.
Okay. Thank you. So we'll be back after 10 minutes for the next session. 10:28. Okay, so let's start the third session today. So am I audible and my screen is visible?
Yes, ma'am.
Okay, so before I start, I send the attendance link. I can see that many of you haven't put this attendance. So please, who are attending, please fill up this Google form. Okay, so let's start. So as you know that today I'm going to, at least today's first lecture, I'm going to talk on cones and their spectral properties. And especially I'll talk about the cone that is related with the semi-positive matrices. So before I start, I already given the this what is a cone?
Hello,
Yes.
Hello?
Yeah,
No,
yeah.
where is the Google form actually? Where I have to find?
No, I say I dropped it on the message message box.
Oh, chat box.
Yeah, on the chat box. Yes. If you join late, then you can ask someone. Or Ecto, can you please copy and paste the link?
Okay.
Okay,
Fine,
ma'am.
right.
Okay, so let's I was talking about the cones. I think I already given a glimpse of what is a cone and what is the convex cones all look like, how this look like. So today I'll start with a little bit of that one, just to recall that what is a cone and a little bit of background, what are the things I will be requiring. And then I'll be talking about the semi-positive matrices. You already know many things about the semi-positive matrices, but especially wanted to talk about the cones, which is related to the semi-positive matrices. So that's the goal I wanted to discuss. And something is since I'm talking about the spectral, and then we will see that how some of the results on the this spectrum. That's what we're going to discuss it here. Okay, so let's start with the background. So cone already I told. So here one can define it in my last lecture. I talked about the cone in Rn. So but one can generalize it to any vector space over any ordered field. I'll be requiring an ordered field there. So then C is a cone if it contains a ray. So that's what we called it. I hope that you remember. Then what is a convex cone? So that means if it is a convex cone, if we can say that if C plus C is a subset of C. And same generation, that notation, that S, if S is any subset of the vector space, I don't need a subspace, it could be any subset. Then the set generated by S, already you know that I am using this notation SG to denote it the set of all finite positive, I should say all finite non-negative linear combinations of elements of S. So this should be non-negative, I mean, not the positive. Okay, and we know that this was also discussed that a cone is convex if and only if C is equal to CZ. So those are the things I already discussed. I just thought to remind you once again. Few examples of cones. So since here my main concern is to discuss about the cones, so let us see a few examples of the cone. Is first is the only the ray. So you know that if x is any vectors, in now we are in a vector space. So if we are having any vector, then if we consider the ray, then this is of course a cone. Then the second is we can think about the non-negative ortho. So I mean the Rn plus I'm denoting is for the non-negative ortho. So that means all this also included. Fine. So this is positive. So this portion is a cone. And there is another cone which will be calling it as as Lorentz cones, or many people you know it as a circular cone. So what is that? I'll show you the picture after some time. So it is the all elements in Rn such that if you know if I'm partition it, this is the x is the first n minus x tilde is the first n minus one consisting of the first n minus one vector, and xn is the last element. Then it says that this xn norm 2 norm of x tilde will be always less than equal to xn. So you can obviously see that one quick observation that this condition will automatically imply that xn is greater than equal to 0. So that I don't need to impose it here. Okay, so there another interesting cone is the collection of all the positive definite matrices. So all x as that x is a positive definite matrix, then that also form a cone. And something other than the matrices, if we consider all the non-negative continuous functions, that also form a convex cone. So these are some examples. So this is an example which is not a convex cone. If just I'm just taking one ray here, I'm taking another ray, union of these two, then this is not going to be a convex. So that's a non-convex. Now is that so it means that a set, if we talk about a set um, in a vector space, that means that may not be a cone. Then but one can construct a cone. We are calling it as a dual cone. So what is that? Suppose that if V is an inner product space, so that means it has an inner product, then we are having any set. I don't need it to be a cone or convex cone, or no may not have any other properties. Then if we're defining C star is the collection of all element in V such that the inner product of V and W is greater than equal to 0 for all W in C. So if that is happening, so in that is happening, then we can say that this is the dual cone, and that is a convex cone. Fine, one can easily prove that it could be a convex cone. Now, if you look, if you just look at the picture, just to show that how this C will look like, C star will look like. Now, C is this. This is the inside one. This is C. So this is not a cone because it is finite. It cannot contain a finite ray. So this is not a cone. So it has some structure. In fact, this is not even a convex set also, because if I'll take any point here, then okay. So then it's not lying on the cone. So therefore, it's not a convex cone. Okay. Now let us see that what is that C star. So one can easily see that it will cover all the element. It is bigger than equal to, if we think about in Rn or in R square. So inner product greater than 0, inner product, it means there's the angle, cosine of the angle. So cosine of the angle is greater than equal to 0. So that means it should be something like between 0 and pi by 2. That's what you can consider. So that means this is the maximum. So if I can take this line, that means all the point here, it will be lying here. If I'll take this is the other line, maximum one, so that means inside this point will be lying here. So that means basically this is the cone. You can easily see that it will be the entire cone. Fine, this is infinite dimension, of course. So this will be the cone C star, the dual cone of the of C. So that means this dual cone always help us if we are given any set, it doesn't have any structure, so we can always form a cone. Now the question is, if it is not an inner product space, whether that can also be generalized or not. The answer is yes, and that's something the raised representation theorem says, that the inner product we can always represent by a functional. So that's how one can define it. So this is the more general. So, and people are calling it as an algebraic dual of a cone. So that means in that case, this is the C star is the those F linear functional on V such that f of v is greater than equal to 0. So that is the most general definition. So now a cone is called to be a self dual. So I'm considering it as an inner product space. Fine. And after some time, I'll forget about the, rather than considering any vector space, I'll be considering the Rn. Fine. And this is a vector space I'll be considering. And obviously in that case, field will be the R. So that a cone in an inner product space is called to be a self dual if it is C is exactly equal to C star. So one simple example is the non-negative orthon. So if I'll take it, so this ray, so that means if I'll consider this is the one, so that means it will take all these points here. If I'll consider this one, then also it will take all these points. So that means it remains the same. So that is called as the self dual. So that means this non-negative orthon, this is a simple example of the self dual cone. Similarly, the Lorentz cone also, and this semi-positive cone also, positive semi-definite cone also. These are some examples of the dual cone. So now I'll go to some more types of cones. So we will say that a cone is pointed. So if its intersection with the negative of that cone is will be 0, we call it as a solid cone if the interior is non-empty. We call a cone as a proper cone if it is close, pointed, and solid. So it should be a close in the sense is the algebraic is with respect to the standard topology in Rn. So now we are in Rn, because otherwise this closeness, if I am starting with any vector space, then I need some topology over there. So to talk about the closeness. So that's the reason from right now onwards, I'm just considering V to be the Rn. And it's called reproducing. If K minus K is the Rn itself, then it will call it as an reproducing. Then another interesting class of cone, which is a polyhedral cone, it means that it has a finite generator. So that means, see, we say that it is a polyhedral cone. It means that I'm having a finite set x1, x2, xn. So we generate this one. So that means any element on that C, I can write it as a finite linear, positive, non-negative linear combinations of finite elements. So then it is called a polyhedral cone. Now there are in R3 there are few examples of of a polyhedral cone or a non-polyhedral cone. Now see, this is, if we consider the first one, this is not a cone because it is infinite. It should contain the infinite trace, so it's not a cone. So this is an example of a polyhedral cone because it's generated by this vector and this vector. So this is a polyhedral cone. And the third one is also a polyhedral cone because it is generated by this vector. It is generated by this vector, and this is the one can consider it. Okay, so in R3, so these are some examples. Here you can see it has 3 generators. This x1, x2, x3. So it has 2 generators, x1 and x2. So these are polyhedral cones whenever it has a finite. Now it has 4. I can see that one is x1 is here, x2 is here, another will be here, and then this one. So this is also a polyhedral cone. Now this is the cone, which is a circular cone, and which is eventually we'll be calling it as we are calling it as a Lorentz cone. So in this cone, it's it's every element here, every vector on the surface will be a generator. So that means this has an infinitely many generator. So therefore, this is not a polyhedral cone. Okay, so few more. Let us see some properties of the polyhedral cone. Very simple properties of the polyhedral cone. Is the first one is K is a polyhedral cone if it can be written as K is equal to some B into RK. Fine. When RK plus, I already told you this will I'll represent it to is all collection of non-negative elements in RK. Fine. So why this is true? One can easily check it. So polyhedral cone, it means it has a finite generator. So it has a P is a polyhedral cone or C is a polyhedral cone. So it has a finite generator. So let me call the generator as C is generated by something like that, maybe x1, x2, and maybe xk. Then I can consider B to be the matrix this x1, x2, xk. So that means it has a size n cross A. Then definitely this C I can write it as B into R of k plus, because if I'll take any element y in C, I can write it as a positive linear combinations of x1, x2, xk. So I have n, so it means that y I can write it as it's like alpha 1 and some x1 and plus some alpha k and xk, which is equivalent to write down it's like B matrix x1, x2, xk, and this is the alpha 1, alpha 2, alpha k. So this is an element because all these are non-negative linear combination. So this element belongs to RK plus. So that means this is B into RK plus. Okay, so that's a very simple way to express the polyhedral cone. Okay. Again, there is another characterization of the polyhedral cone. It says that it can be a finite intersection of finitely many closed half spaces containing zero. So half space means Ax is less than equal to P. So when it contains zero, so that means zero should be there. It should contains the zero. So it means that if I and on its boundary, fine, it should be on the boundary. So that is another characterization of the polyhedral cone. And next is the polyhedral cones are close convex cone. One can easily check. And if we see the characterization of the polyhedral cone in terms of this dual, it says that the K is polyhedral if and only if its dual is also a polyhedral cone. And we say that this is also another one reproducing a close convex. If we start with a close convex cone, and if it is a solid, so that means if it has a non-empty interior, then it will be a reproducing. So that means entire Rn we can write it in terms of K minus K element. That means one element from the cone K and another element from the cone negative K. So another characterization is that this will be reproducing if and only if that K plus or K star dual is solid. The reason is if it is reproducing, then it says that this will be I'm starting with an of course a close convex cone. Then this is a solid. If it is a solid, then K star is also solid. Okay, so these are few properties about these polyhedral cones. So now another important concept or another cone, another type of cone that I'm going to consider it here is the simplicial cone. And for that is I need the concept of extremals. And another question is I told that here the polyhedral cone, it means it has a finite number of generators. So what is these generators are? And these generators are called as an extremal. So let us see the definition. What is an extremal? First of all, one we can see that if we are given a cone, of course in Rn, so then this always defines a partial order. And how I'll be defining it? A less than y. The definition is A less than y implies by x minus y will belong to k. No, it should be y minus x, I think. Yeah, it should be y minus x. Huh? Y minus x will belong to k. So one can see that this is symmetric. This is reflexive. This is antisymmetric as well as this is transitive. So one can see that this forms a partial order. Now, what is an extremals of a cone? So a vector in Rn is said to be an extremal of the cone. So one thing you note that it can be an extremal can be any vector in Rn. It may not belong to the cone K. So that vector is called an extremal if this relation happens. So that means if y belongs to K, x minus y belongs to K, then that will imply y is nothing but the ray is y is exactly equal to alpha into x for some alpha greater than 0. So that means y will be lying on the ray fine generated by x. So in that case, that is called an extremal. And if we consider this ray, so x of g, if x is an extremal vector, then this ray will be calling it as an extremal ray. So now if you can see this picture, it's okay. It says a pointed cone. No, it didn't come entire one. Okay, this is a cone. So then these boundaries are nothing but the extremals. Fine. One can easily check that the extremals are always lying on the boundary. It cannot be lie inside the cone. So this is the boundary. The extremals are these are the extremals. Fine. So these are the boundaries which help us to generate the cone. So and one can easily prove, and it's been proved by Van der Graaf in 1968 that a proper cone is always generated by its extremals. If you are having a proper cone, proper means it should be pointed, close and solid, then this is a proper cone. So it is always generated by the extremals. And since a polyhedral cone is a proper cone, one can easily check that a polyhedral cone is a proper cone. So that means it is generated by its extremals. Now, a particular case of polyhedral cone, I'm calling it as a simplicial cone. It says that a proper cone in Rn, if it has exactly n extremal rays, then this is called a simplicial cone. So it cannot be more. Now, if it is, now look at here, suppose if this picture is, we are in the 3 dimension. So that means it has how many extremal rays? 1, 2, 3, 4, 5. So it is more than 3. So that means this is not a not a simplicial cone. This is a polyhedral cone, but not a simplicial cone. So if we go back to here, now look at this one in 3 dimension. If you see, this is the first picture. So you can see that there are exactly 3 numbers of extremals are there. So that means this is a nice example of a simplicial cone. Neither this is a simplicial cone, which is an example of a polyhedral cone. And since this is not a polyhedral cone, therefore it cannot be a simplicial. No point of thinking about whether it is simplicial or not. So now, because we have seen in case of polyhedral cone, so we know that it can be written in terms of the C is equal to B and RK plus. Now, if it is a simplicial cone, suppose if I'm saying that S is a simplicial cone, then what is this form? So it can obviously, we can write it as B, then this should be Rn plus, where B is an n cross n and it should be invertible. Okay, so it should be an invertible matrix. So here the B was a non-square matrix, and here it is a square matrix, and eventually this is an invertible matrix. So that's what has been written. This is a non-singular invertible matrix of order. So in R2, if we are in R3, I have given you examples that we have polyhedral cones, which is not a simplicial cone. Already it's been drawn there. So now, but in R2 we cannot find out. In R2, all the polyhedral cones are simplicial, and all the simplicial cones are polyhedral. Fine, those are same in R2. Now let us revisit this semi positive matrices. So this semi positive matrices, but we will revisit it in terms of the semi positive cone. Fine. So what is that? Let me just see. I don't want to go through it. So you already know that what is a semi-positive matrix. It means that there exists an x greater than 0, or I can consider is strictly greater than 0 or greater than equal to 0, such that ax is greater than 0. Then minimally semi-positive, already been discussed that it should be a semi-positive, and if we delete a column, then it will be no more a semi-positive matrix. And what is a redundant semi-positive matrix? If it is not a minimally semi-positive matrix. That means semi-positive matrices, we can divide it into 2 classes. One is the minimally semi-positive matrices, and another is the redundant semi-positive matrices. Okay, so we know all these things, that how it is related with how the semi-positive matrices is related with the LCP. So those are the things already known, and this theorem of alternative is already been discussed by Michael in the previous class. And this characterization of minimally semi-positivity already been discussed, that in square matrix is minimally semi-positive if it is if and only if it is inverse positive. Okay, so Mike, as I told you that here semi-positivity, we will discuss it, but in terms of a cone. So now suppose every semi-positive matrix always generates a cone, and that cone will be calling it as a semi-positive cone. And what is that cone? So I'm writing it in this form. So K of A, so such that x is greater than equal to 0 and x is greater than equal to 0. Why this is cone? Well, you can easily check that why this is the cone. And this cone is in terms of the, if we wanted to see in terms of the LCP, because here is the the main goal of our this course is that we need to see the relation between the class and matrix classes, which help us in solving the LCP. So you can say that in terms of, if I wanted to see in terms of the LCP, then KA is all the solutions of the LCP with Q is equal to 0. One can easily check. This will be an one line proof. And the second one is the interior. So now K is those x greater than equal to 0, such that Ax is greater than equal to 0. So the interior is those x strictly greater than 0, such that I can say that Ax is greater than equal to 0. So if we start with a semi-positive matrix, so which assures us that there exists an x greater than 0, such that Ax will be greater than equal to 0. So it means that the interior is non-empty. So it shows that Ka is solid. And one can easily check that this is the closed convex as well as this is pointed. So therefore, a consequence of all this, we can say that K is the proper cone. Now let us see some of the properties. These are the properties. I mean, you can find out in Professor Shivakumar's and Michael paper is the semi-positive matrices and the semi-positive cone, and that's very interesting. And that's they did it for the first for non-square matrix, square matrix, and then they generalize it for the square matrices. So it's the properties about that how this the relation with the semi-positive matrices and its cone K. So it says that if we are having a semi-positive matrices, then it's dual. It is of this form. So A transpose Rm plus Rn plus. Okay. So from here, one easy consequence is that one can check that this is a proper polyhedral cone K. Already proper, we already been seen that is the proper cone, but from here we can see that it is a polyhedral cone, because one property we have seen that K is a polyhedral cone if and only if its dual is a polyhedral cone. And its dual, this is a polyhedral cone, we can easily check that this Ka star or K will be the intersection of two polyhedral cones. In fact, this is the Rn plus and the cone generated by the Coulomb survey. One can see, but that the proof, if you can look at the proof, they have done it that they proved it that K star is a polyhedral cone, and since K star is a polyhedral cone, therefore K is a polyhedral cone. Another very nice consequence of that is that this is a self-dual cone if and only if it is a non-negative matrix. So these are a few interesting results which is related to the semi-positive cone. So now there is another cone which we don't need a semi-positive matrices. So that means if we are given any matrix, we can relate with a cone, and we'll be denoting it by S of A. And what is that? It is the collection of all x in Rn such that Ax is greater than 0. It should be greater than equal to 0. All x, it should be greater than equal to 0. Otherwise, it zero element may not be here. So it's all elements such that x is greater than equal to 0. So it means that one can easily say that the K is nothing but the intersection of is SA intersection Rn plus. And in 2020 we have proved that that if we are having an invertible matrix, because this SA can be defined for any non-square matrix, and especially the results here, it shows that the K is a polyhedral cone. This result will motivate us to see that the properties of SA. So if it is not a semi-positive matrix, then we cannot talk about the K, because it can be empty set also. So then there's the reason this SA has been considered, and here we prove that if we consider an invertible matrix, this SA is not only not only a polyhedral cone, but it is a simplicial cone, right? So if it is simplicial cone, so obviously something will be coming to our minds, and then what will be its extremal, how its cone has been generated. So and it's been there on that particular paper. One can see that that is generated by the I haven't write down it. Okay, that is generated by actually the columns of a inverse. Fine. So the proof you can find it. I haven't write it here. So because a inverse is exists, so if we take the columns. So sorry, no, that cannot be, because unless it is an so here it's something different. It is, I'm talking it about this something else. So no, here it's what is this xn? So it is this extremals will be all the xn, x1 x2 xn, which satisfying this one, where ax if we'll apply to this xn, which will go to this x's. So those will be the extremals. Okay, so the next question is that is the relation, because what is that we are given a invertible matrix, and we found a simplicial cone. Now it's about the convert. So that means it's quite obvious question that if we are given a simplicial cone, can we find out a matrix such that K will be SA? And the answer is yes. And here is the theorem. So it says that if K is a simplicial cone, so we can always find out an invertible matrix A such that S of A will be K. And what is that matrix? If you are curious about that matrix A, so then you can see it here, because if it is simplicial cone, so we can write it in terms of K is equal to B of A, and then B is nothing but is an invertible matrix. That also we have seen it. So then if we'll take the A to be the inverse of B, then that A, for that A, SA will be the K. And what will happen if that K, if it is lying on the non-negative ortho, then in that case that K will be, we can find out the minimally semi-positive matrix. Fine, we can find out the minimally semi-positive matrix such that K is equal to Ka. Fine, then in that case that minimally semi-positive matrix set SA and K will be the same. Okay, so this tells us an one-to-one correspondence between the simplicial cones. If we'll consider the collection of all the simplicial cone, and if we consider the collection of all the invertible matrix, then this gives us a one-to-one correspondence between that two. The next concept is the cone preserving matrix. So what is that? So suppose we are having a cone K, proper cone. We'll start it with a proper cone K. So if you want to remember, so it has non-empty interior, pointed, closed, and convex. So then pi K, what is that set pi K? Is the collection of all the n cross n matrices which leaves the cone K invariant. So it means that A of K is a subset of K. Now let us see a particular case. So if we'll take K is equal to the non-negative ortho, then what is that pi K? So in that case, pi K will be the collection of all the non-negative matrices. Now this is because there we can find relations between pi K and this is the non-negative matrices. Find that K and pi K and the non-negative matrices, because if we choose a particular K, then this pi K is becoming the collection of all non-negative matrices. And whenever we're talking about a non-negative matrices, we cannot avoid the Perron-Frobenius theorem. And what it says, I guess all of you know. So it says that if we are having a non-negative matrix, of course I'm talking about a square matrix. So its spectral radius is greater than 0. It's an eigenvalue, and we can always find out a non-negative eigenvector. And if A is irreducible or positive, then this rho A has algebraically simple and therefore geometrically also. Now, this theorem holds for the non-negative matrices. And in the previous slide, we have seen a relation between the non-negative matrices and the matrices that leaves the proper cone invariant. So that means this Perron-Frobenius theorem can be generalized for this pi K matrices. And let us see what is that. Okay, so you can see that this is quite an old paper. So it's been published in sometimes in 1967. So this okay. So this gives us the generalizations of the um, what is the parent Frobenius theorem. So first thing is that suppose you started with a proper cone, fine, and if A is in any matrix in pi k, so that means if A is any matrix which leaves the cone k invariant, then for that matrix row A will be always an eigenvalue, fine. And second thing is what can happen. So if lambda is any eigenvalue such that whose absolute value is exactly equal to the spectral radius, then tau a, what is the tau a? Tau a is the is the, oh sorry, this should be the a, huh? This should be a, not t. So tau a is the size of the largest Jordan block that associated with lambda, fine. So that means better I should write down it in this should be a, I mean, this should be a correct probably. So I mean that the tau, but with respect to lambda a, fine. So maybe that's the, this is also I haven't write it correctly. Maybe tau of a. So that probably the correct one. So that means this is the size of the largest Jordan block with respect to the lambda, fine. So then this will be, it says that the tau of lambda, size of the largest Jordan block, will be always less than equal to the size of the Jordan block, largest Jordan block, which is associated with rho a. And what about the eigenvector? So eigenvector, yes, we can find out an eigenvector x which is in k, fine. So that eigenvector is associated with this spectral radius, fine. And very interestingly, that this converse of this theorem is also true. So that means if I am having a matrix with satisfying these three properties, then we can always find out a proper cone such that A will belong to the that pi k. So that is something, very interesting. This converse is also true. Okay, so since I'm talking about the pi k, so let us see some of the special cases. Fine. So this is special cases because we are mostly dealing with the semi-positive matrices. So and we are talking about a square matrix. So if we start with a minimally semi-positive matrix K, then Ka, this is the semi-positive cone that is associated with the semi-positive matrix A. Then the pi K, it is a simplicial cone. So then there is a proof here. So simplicial cone means you see that pi k. So this is if A is an n cross n matrix, so then this is a this is a subset of R n cross n. So that means it has any square extremals. And what is those extremals? If you are curious, then it's been defined by this. So that means I consider what is A. So yeah, for a minimal I think I skipped that one. I forgot to include it here. So one can check that or it's been proved from the same paper that if A is a minimally semi-positive matrix is, then K is also simplicial cone, and its extremals are nothing but the columns of the A inverse, fine. So here and here this matrix is A till uh, A tilde I, these are representing the columns of A inverse. And suppose that BI transpose represents the rows of A, then in that case, BPQ defined by A tilde P and BQ transpose, these will be the extremals. Now, the generalization of the semi-positivity. So, how one can generalize the semi-positivity in terms of the cone? So that can be done by in terms of the two proper cones. So if you are having two cones, a proper cone, suppose that I'm denoting it by K1 and K2. So it can be the first cone I'm taking it in Rn, and the second cone I'm considering it on Rm. So then a matrix A in M cross N matrix, real matrix. So we are calling it as an as a K1, K2 semi-positive if there exists an X belongs to K1 such that AX belongs to the interior of K2. So then this is a we're calling it as a K1 K2 semi-positive matrices. Now if we go back to our definition of the semi-positive matrices, so in that case we are taking this K1 to be exactly equal to Rn and the K2 to be exactly equal to Rm. So in that case, so that means this is Rn plus. I mean this is Rn plus. This is also Rn plus. So what it says that in that case there will be an X which belongs to Rn plus, so non-negative orthen. So that means X is greater than equal to 0, such that Ax will be the interior of the K2. So when it belongs to the interior, so that means Ax will be greater than 0. So that means this is the generalization of the semi-positivity in terms of the cones. And people are working on that. Many you can see many work. So another thing is that if two cones are equal, so K1 and K2 are equal, so then we are calling and suppose that I'm writing it as K1 is equal to K2 is equal to K, then this is called a K semi-positive matrices. Now you can see the many papers people are still working on the semi-positivity with respect to the Lorentz cone, Ln plus semi-positivity. Then there are some still research are going on this Sn plus semi-positivity, where Sn plus is the cone of all positive or positive semi-definite. Okay, these are some ideas where we can generalize the concept of the semi-positivity in terms of the you know in terms of the cones. Fine. So that's all that I wanted to discuss. References I already mentioned it here. So wherever I used it, all the references I pointed out as a footnote. So that's all that I wanted to discuss here on this lecture. So in the coming lecture, you can see the topic that I'm going to consider it here. It's a sign pattern of semi-positive matrices. So before I'll take a break, so I just wanted to see if you have any questions or any comment or you want to ask anything.
Excuse me. You discussed the class of semi-positive on a cone.
Yes.
So, can we use this concept for other classes which were discussed by Michael, sir? Is there any
that discussed by, for example, semi-positivity. If you are thinking about the P matrix, then is the determinant. Determinant is non-negative. So how we'll be generalizing it? So that
like you using some kind of characterization that he gave in morning, like
so
for
that
any
the reversal one that doesn't reverse the sign of a non-zero.
Right.
I don't know for the no, I didn't see. The reason is I'm not sure, but I didn't see any generalization. Again, if you go back, it's been many generalizations, many characterizations was given by Michael, but I cannot able to think here for a proper cone. Suppose if we'll go for this if we'll go for this reversal one also, so that means for all x not equal to 0, greater than equal to 0, so there exists an index I. such that xk is greater than 0, and then this is xk, and then axk will be positive, so it doesn't change the sign. Could be, but I'm not sure. I didn't know it, that if there is any kind of generalization, at least for the P matrices. But for M matrices and all these things, though, I know that people are still working. Z matrix, M matrix, they have this concept of this.
And what about the class of semi-monotone and strictly semi-monotone?
Yeah, that's the same thing, because if we're talking about here only that will be the same thing. So no knowledge on that. But
Okay.
I know that for the M matrices and for the Z matrices, they have something. In fact, if you're looking for the generalization, there are more generalization of the semi-positivity also, and one can instead of the Rn, because here it's also very specific. The cones we consider in Rn.
Mm-hmm.
So that is something, I'm also looking for some areas there. Is instead of the Rn. If we will consider Rn plus, Euclidean matrix or Rn, what will happen if we'll consider this Euclidean what is that called? If I mean, what's that particular? I could not able to recall. It's an let me see. I have it. Just give me a moment. Do I have it here? It is where it is. I cannot find it here. Maybe we can find it here. Just give me a moment.
Okay, ma'am.
I wrote it before in that slide, and then I thought that will be taking much more time, so I deleted that slide. It's about some future direction one can go ahead.
Okay. So
it's
in
like
you can share that.
Okay, it is like it's like an Euclidean Jordan algebra.
Okay, what is?
So because Rn is also an Euclidean Jordan algebra. Okay. So Euclidean Jordan algebra is something. It is something with respect to inner product space.
Okay.
So I started with an inner product space, and then there is another product that will be defining it. So which is I'm denoting it by dot. So this is also from V to V, and it's satisfying. That means if we are having an xy, then it will go to x circle y. So that means V is equipped with two operations. One is the inner product, and another is that we call it as an Jordan product. And with respect to that, it's satisfying some conditions. First is your x circle y should be commutative. Jordan product should be commutative. The second one is it's x circle x square, then y will be exactly equal to x circle x and y. So this is here. What is that x square? I mean that, of course, x not x. And the third one, it is the relation with this Jordan product with the inner product. So that means x circle y z. This will be y circle x and then z. So if these three conditions, B is an inner product space, and if we can define it to be the dot product, I mean, so V to V, fine. So then this is called an Euclidean Jordan algebra. And one can easily check that this Rn is an Euclidean Jordan algebra, where this is, you can take it to be the entry-wise product. So that's the reason, that is something is coming to my mind, that whether all this concept instead of the Rn, whether all this concept of the cones and everything can be generalized into the Euclidean Jordan algebra and later.
Is this new in literature? Because I never heard about it, Jordan.
No. It's because maybe the reason, because I was also not aware of that until I joined some some of the seminars, it's people who are working on especially on the Euclidean algebra, Jordan algebra, it's abstract algebra, then it's quite familiar. This is not new. This Euclidean Jordan algebra is quite old, but now people are joining these two concepts. I mean, this this cones and then with the Euclidean Jordan algebra.
Okay, ma'am. Okay, thank you.
Hello.
Yes.
Can you please go to the slide where to reduce that semi-positive matrices generate a cone?
Semi-positive matrix generates a cone. Okay. It's here?
Yeah, ma'am. This KA
Huh.
equals to. So yeah, my first question is that this equality of LCP equals 0. So how are we going to the x and ax are orthogonal? If x in KA.
No, the LCP, if I just wanted to write down again. So LCP of, suppose that this is, I just wrote it in opposite way. It should be 0 and m. No? That's what I use it. LCP will be the 0 and the a. So if you recall that if it is q and the m, then we can talk about this. That's what, no? X transpose ax.
The orthogonal, what are we going to get that?
Yes, that. I think that is yeah, that's correct. So it will be first two things won't be a problem because of q is equal to this should be positive. Q plus mz should be positive. So therefore here this is okay. Q is 0 here, and then the next one will be the z is 0, and no, what this is this should be z is 0 na here. No, what is that? Q is 0. Sorry, Q is 0. Yeah. Yes. So only problem is will be that this one na z transpose and then
orthogonality of
orthogonality of z transpose of AMZ will be is greater than 0 or not. Where from this is coming?
Yes, we have to 0. So how is it going to be?
I think it's coming from this one, but I'm not sure, because for the semi-positive matrices, if it is satisfying the first two conditions, it may not be. Yeah, of course, it may not be. These additional conditions may not be satisfying. I can say that only the solution of the first two, the last one, if we can that exclude. Yeah, that may not be the it may not be.
Maybe that the equals 0
No, okay, so I cannot hear you. I'm not sure whether it's my connection is a problem or yeah, can you say? Yeah, Shonali.
Yes, ma'am. Can we say that Ka is equal to feasible set of
that's
0,
what.
A?
Yeah, that's what I just said.
Yeah.
That it probably will be only for these two first. That's what. Yeah, that's
right. So it should okay. Then it will be a feasible set. Okay.
Yeah, it's just
feasible solution. Yeah.
Maybe I should not write down
another question.
Yeah.
Similar to this positive matrix generate cone. So can we say that P matrices or the semi-monotone, strictly semi-monotone matrices also generates a cone, or can we say anything about those matrices?
No, that's what I think. I didn't heard about that, because the only concept is how we are going to relate that one. Because in terms of the positive, this M matrix, P matrices especially, or the semi-monotone matrices, It's not sure that I don't have any idea whether it's still people are working on that generated the code. So I don't know. I mean, I'll see if I can find out some article. Then maybe I'll forward it to you.
Yeah, ma'am. That's all from my side. Yeah.
Okay.
Okay.
Okay. Anything else? Okay, then maybe we'll take a break of 6 minutes and we'll start again at 11:30. Hope that will be okay.
Yes, ma'am.
Okay, then see you after 5 minutes. Okay, so let's start. So this will be the last talk of my last talk of this course. So here I'll be talking on the sign pattern of semi-positive matrices. Okay. So let us start with the basically I'll talk about first. I'll start with some basic definition that is related with the sign pattern. What is a sign pattern? How is it defined? And then in particular we'll be discussing the sign pattern of semi-positive matrices, then some sign pattern of minimally semi-positive matrices and redundantly semi-positive matrices. So these are the three cases that we are going to consider. So let us see that what is the sign pattern means. So an M cross N sign pattern is an M cross N matrix. Right? So this is a matrix whose entries are the symbols. So this is not the entries from here. Whose symbols are either it can be 0 or positive or it can be negative. And we say that a sign pattern is full if each entry is either 0 or negative. So that means it cannot have a zero symbol on that particular matrix. Then we are calling it as a sign pattern is full. Now, if we are given a real matrix, I cannot talk about the complex matrix because yes.
Whose entries are symbol 0 plus minus 1 or plus 1 minus 1?
No, only plus and minus. Not these are symbols, not the elements.
Okay.
So it means something like that. I can say that this is plus, this is minus, and 0. This is plus, then this is 0, maybe minus. Right? So that's the reason many people they don't call it as an array instead of the matrix. Many people that's why they are calling it as an array of symbols. Okay. So now if we are given a real matrix A, then we say that it has a sign pattern B if A and B are of same size and A of ij is equal to 0 when Bij is equal to 0. Aij is positive when Aij, if Aij is positive, then Bij is equal to plus. Aij is negative, so that means Bij is minus. So then we'll say that the matrix A has a sign pattern B. So it means that it's very so it's very simple. Suppose that if I have a given a sign pattern matrix, maybe plus negative 0 and then 0 0 2 by 2, then if I'm calling it as in B, then I say that a matrix A has sign pattern B if this entry, if the related to this entry, it should be positive. So that means this is a positive entry. So A11 should be positive, and here A12 should be negative, and this should be 0. Then all these matrices, if we consider the collection, these matrices we call that this matrices has a sign pattern B. So B is basically a sign pattern matrix. Then the next one is what is a realization? So a realization of a sign pattern, this should be sign pattern matrix. So this I missed it. Of a sign pattern S is a real matrix that has a sign pattern B. For example, in that case, if this is the A, then and if this is the B, so B is a sign pattern matrix. In that case, we say that the this has a realization of a sign pattern of S. So that means if this is a real matrix, sign pattern a realization means it is a real matrix which has a sign pattern B. So that means this particular A, so this particular A or A tilde I'm calling it as it, then this A tilde is a realization of the sign pattern matrix B. So that means in a realization is all the matrices which has the sign pattern B. So then that is called the realization. Now, suppose next is that's something important, and that's what we'll be calling it as. So throughout this my talk, I'll be using the character S to mean it as a sign pattern matrix. So it says that if we have a property, let me call it as a property P. So then if a matrix may have the property P, then the sign pattern S, we say that the sign pattern S allows P, so that means P is just a property of a matrix. So then we say that the sign pattern S allows P if there is a realization S that enjoy the property P. So then in that case, we say that the sign pattern is that allows the property P. So P can be any property, fine. So suppose that P, the property, I'm calling it as a non-negative property. So then suppose we are having a matrix having a property. Suppose A is a non-negative matrix. Then a sign pattern matrix, it says that that S will allow non-negativity if there is just a matrix, fine, which has a sign pattern S, and that is also non-negative. So in that case, that is an example of an S allows the property P. So there exists a matrix. And similarly, we can say that the sign pattern S requires P. Fine. If each realization of S enjoys P, so that means if realization means each realization of S means that every matrix that has the sign pattern S also has the property P. In that case, we'll be calling it as the requires. If there exists one, then we'll be calling it as the allows. And if it is happening for all realizations, then we're calling it as the required. So here basically when we're talking about the semi-positivity, I said that the sign pattern of semi-positivity. So that means we're calling the semi-positivity as a property, and then we're talking about the that allows the semi-positivity or that requires the semi-positivity. Fine, those are the properties we'll be talking about here. Okay, so before that, maybe I'll be requiring few more definitions. So first one is complementary. So what is a complementary? So a full sign pattern. So M cross in full sign pattern. So that means it cannot have a zero symbols. So then that full sign pattern matrix is called complementary if we are able to find out a subset alpha of 1 to m and beta from 1 to n, such that at most one of them alpha bar, beta bar, this is backslash, I guess I missed it. So this is beta bar. So at most one of them is non-empty. What is alpha bar? Alpha bar, I means that this set, complement of alpha on this set. So beta bar, I means that the complement of beta in this set. So that means at least one of them set should be non-empty. Fine. And such a pair, when such pair exists, we call the such pair is called as a proper. Such that the submatrix I considered is alpha and then beta bar, that consisting of entirely negative signs, and alpha bar beta consisting of entirely positive signs. So it means that it's like I'm having a matrix. This is an any size, fine, any size. So that means we can make some kind of partition kind of thing here. So this is alpha bar, and if it is beta, and then this is beta bar, then it says that the matrix, so this matrix alpha beta bar will be all negative. So alpha beta bar, so that means this portion, correct? So this submatrix is all negative, all the signs are negative, and this submatrix which alpha bar and beta, the next one is alpha bar and beta, this is consisting of all positive. Then that sign pattern, it should be full, so there should not be any zero. Then that sign pattern, we're calling it as an complementary. So if S is complementary, I just shown that we can see that we can always do the permutation of the rows and the columns, and eventually we can bring it in terms of the this will be the negative. This portion is, we can always do it. So this portion is always negative. This portion is always positive. Fine. So that can happen. And if this is happen, if none of them are non-empty, if one of them is empty, then this will be either of this form. Fine. If suppose that if it is if this is one by one, only the alpha and alpha bar it has, that means it has the this beta and these things is not there, beta and beta bar, so that means it is the plus. This will be star and this side is positive. Similarly, this side, left side is positive. Here the left side, if it is the first case, then it will be the first half. If it is the second one, then it will be this case. And row wise, it will be column wise, it will be this portion, or this is the one. So these are the only possibilities that can have when it is the sign pattern is complementary. So now let us see the sign pattern of the semi-positive matrices and what is that. So first thing is the property. I'm calling it as the property is the semi-positivity is the property. Fine. So then here it says that the assign pattern that allows semi-positivity if and only if each row of S contained a positive. Fine. So S is a sign pattern, and that positivity. Allow means what? Allow means there exists a matrix. Fine. There exists a realization such that whose sign pattern is S. Fine. There exists a matrix whose sign pattern is X, and that is also preserved. That is also semi-positive. Fine. So that's what I mean, that S allows a semi-positivity. So let us see the proof why this is true. So first thing is that if and only if each row contains a positive. So suppose I'm assuming this condition. Suppose that S is a sign pattern matrix. So that means S has all elements can be either plus or zero or negative. Fine. So now each row, suppose that I'm assuming that each row contains a plus. So at least one plus is there. Then we can find a realization. So that means we can find out a matrix A which has the sign pattern S. S is given. In which, so we can always, if we are in these examples, we know that if we are given a sign pattern, we can always find out a matrix which has that sign pattern. Fine. But here on the top of that, what else we wanted? We want that we find out a matrix which has the same sign pattern and having this property that this we can find a realization matrix in which these positive entries are large enough. This means that the where the plus is there. Fine. So what you can do, so what I mean it, so let me just tell you. So I have a sign pattern. So let me erase this one. Yeah. So I have a sign pattern matrix. So maybe each row says that it is an each row is it should be a positive. So it should be positive. Each row has a positive. So this could be a negative element and this could be a zero element. So we can always find out a matrix which has this entry. So that means here A11 is positive, A12 is negative, this is zero, and here I can find out to be A22 to be positive. So all these matrices has a sign pattern A. But what I'm saying, I can choose that wherever this each row, wherever it is positive. So here A1 is positive, here A22 is positive. I'll choose these entries to be very, very large. Fine. If I choose this matrix to be very, very large, then what can happen? And this I can make it as a small. We can always find out. And in that case, what can happen? See, if for such a cases when this is very large enough, then if I choose an x1 and x2, then this is a large enough, and rest are where this is negative or zero, they are small enough. So that means this will eventually it will be becoming x11, a11, then plus a of 1 to x2, then this is 0, and then a of 2 and then x2. So in that case, this we can always find out the x1, making it to be the large, and this is to be the small, so that this is positive. Fine. And similarly, we can find out this is positive. 0 cannot be there because each of the column is always contained a positive entry. So that means in that case, this matrix, the matrix what we found it, that matrix is a semi-positive matrix. Fine. In fact, that's what I'm saying. In fact, you can do it. You can choose U1, U2, or you can take in particular 1 1 if you take it. So that means A of E is 1 1. So that means this is eventually coming as your A 1 1 plus of A 1 2. This will be the A 2 2. So that means this is a row sum. Now, since this is positive, so I can make this to be large enough to make it positive. I can make it this large enough to be positive. So therefore, this shows that this A is a semi-positive matrices, semi-positive matrix. It means that this sign pattern allows a semi-positive. That means we are able to find out a semi-positive matrix which has a sign pattern S. So similarly, one can see the converse is also true. If it is semi-positive, if we have a sign pattern that allows semi-positivity, then each row of S also contained a plus. So why this is happening? Suppose that each row, suppose we are having, so we'll prove it by the method of contradiction. Suppose that there is a row which contains only the 0 and the negative element. So that means it doesn't have a positive sign. So then for any x greater than 0 and for any realization S, then the ith entry, because this ith row is contain all the negative or 0 element. So here, whenever I'm doing the multiplication, so this is A, so this is the ith row, and this is the x1, x2, xn. So whatever the positive x1 I choose it, here all are negative or 0. So that means this will multiply by here, so which will gives you the A of ith element. So that means this will eventually become a negative or a 0 element. So that means in that case, it cannot be a semi-positive matrix. So this is a very, very simple proof. So that's about the, allows. Now it's about the requires. It says that if S is a sign pattern that requires semi-positivity, so that means if we consider any matrix which has a sign pattern S, then that should be semi-positive, semi-positivity. Then what is happening? Then S has a column in which each entry is non-negative. So that means that case sign pattern should be one column. We should able to get it here, which is consisting of either plus or 0. No, it cannot contain any negative sign. So that is also very, very simple, and that is also suppose that one can see that suppose that it has a it shows that S has a column. No, S has a column. Suppose that all the columns has a negative entry. Fine, each column has a negative. So then we can find out in the same way that we will do it. We can find out a realization in matrix which has a same sign pattern, and the column sum we can make it to be the negative. So that's one we can do it. So in that case, E transpose A is negative, and therefore if we choose any x bigger than 0, then E transpose X is also less than 0. So E transpose X is less than 0. It means that the sum of the entries of AX is less than 0. Fine. So it, and which will imply that AX is not a positive vector. So that means it should have a negative entry. Fine, because sum is the negative. So that means S does not require the semi-positivity. So whenever it requires a semi-positivity, that the sign pattern always contains a column such that which doesn't contain the negative sign. So that's all. Maybe we wanted to. There may be, because this is not an if and only if condition. This doesn't characterize that what is the sign pattern request for semi-positivity. So for the characterizations, I'll be requiring a few more definitions, which will be very, very simple. So first of all there's the form G. So what is that? We say that a sign pattern S is said to have form G if each row has a non-zero entry. So each row must contain a non-zero element. That means It cannot happen that the sign pattern will have all the 0 entries. And the rightmost one, so that means I'm talking about the rightmost one means rightmost non-zero entry. So rightmost non-zero one is being positive. So extreme rightmost one should be positive. Now, if you look at here, all the column, now star can be anything. Star means it can be positive, it can be negative, it can be 0. Now all are does not contain the 0 row. Now what has happened? The rightmost, if you look at the first column, the rightmost one is, this is the plus. So I mean the non-zero, rightmost is the non-zero. So this should be always positive. So here also look at the next column, the rightmost one, this is positive, and the last one is also positive. And then what next? It says that in each row, after the first rightmost non-zero entry occur in a position not to the left of the rightmost entry in the preceding row. So it means that in the simple word, I can say that the here will be occur on the right side of the previous row. So similarly, this is the one. This is the one. Okay, you know, it's some kind of, if we remember our row echelon form, then it is some kind of, you can relate with that. Okay, so this is just an example. This is a form G. So in that case, this is called as a form G. Now the rightmost top entry in a row of a sign pattern matrix having the form G is called the front plus of the row. So that means this is, I'm calling it as a front plus. So it can so happen. See, this could be also positive. So this particular element, I'm calling it as a front plus. This is front plus. This is front plus. And what is a generalized positive column? So I'm not talking about a positive column, but this is some kind of generalization of the positive column. And what is this? A generalized positive column is a sign pattern S which is permutationally equivalent to the sign pattern having form G. So it means that if we are given a sign pattern, so that sign pattern we call it as generalized positive column. If we can able to find out two permutation matrix P and Q may be different, that means we can permute the rows and columns, and eventually by doing the permuting the rows and columns, we can bring it into this form. Then we call it as a generalized positive column. Okay, so then this generalized positive column, this gives us the characterizations of the sign pattern that requires semi-positivity. So that this theorem says that a sign pattern this requires semi-positivity if and only if that generalize the positive column. Okay, so maybe I kept it here. There is another characterization of the sign pattern matrix which requires the semi-positivity. So then now I would like to move to the next one where we can define it to be the sign pattern of the minimally semi-positivity matrix. So that means the sign pattern that allows the minimally positivity or that requires the minimal positivity. I'm talking about in terms of the property. So to start with that, let us see a few things which I'll be requiring. This is B12. Okay. First is this is what I, okay. So these are few one theorem. So this is few results. Okay, few results. So before I start with this our result, let us see few results on the sign pattern matrix. So this is the first result. It says that if B is a sign pattern matrix or S is a sign pattern matrix, then there exists the inverse positive matrix A of order n with the sign pattern B. So B is any given matrix. It says that there exists an inverse positive matrix which has a sign pattern B if and only if B cannot be permuted by independently permutation of rows and columns. So that means the permutation doesn't matter. I can permute first and the second rows, and I can permute the third and the fourth row. So those are independent, such that it can be of this form. So B1, so what is that? Says that this block should be entirely negative. Fine. Oh, is that B or? Yeah, that's B. Yes, that's correct. So this is B. B is negative means all are negative. I mean that I wrote it here sign negative, but what I mean that these are all negative, and these are all positive, and this could be anything else. Fine. And what X is one of them B11, B12. So it's been one of them B11 and B of 12, and so all this. So one of them should not be non-empty. So now if you look why this is why I'm saying that one, because whenever we're talking about a inverse positive matrix, and we know its connection with the minimally semi-positive matrix, and that's the reason this has been written. And this sign pattern, if you just see this one, the one I have written, that is nothing but the is not a complementary. Fine. So that means it says it is a complementary, but it cannot be. Fine. So that means this B is not a complementary. So that means if I wanted to conclude from here, I say that if we are having a full sign pattern matrix that allows inverse semi-positive matrix, allows means I should able to find out one minimally semi-positive matrix, and minimally semi-positivity means that is equivalent to say that A inverse is positive if and only that sign pattern is not complementary, because this is an example of an complementary sign pattern, but I say that I cannot find out, so that means we cannot have this non-complementary sign pattern. Okay, so here we have seen that this theorem is if you wanted to find out, you can find out on this particular article, which is by Johnson. Okay, so now here one thing, observe that this theorem is only for the full sign pattern. Full sign pattern means it cannot have the zero. Now, whether the question is whether can it be generalized for any sign pattern, the answer is yes. And here are some of the results that is related with that sign pattern of minimally semi-positive matrices. Now, suppose that I'm allowing that any sign pattern not necessarily to be a semi full. Okay, then that sign pattern allows minimally semi-positivity if and only if S is permutationally equivalent to an upper block matrix. Fine. So that means I can do the permutation, permutationally equivalent, row permutations and column permutations, same permutation. Okay. So we can do permutational equivalence. So row as and columns, I can do the permutation, not necessarily to be the same. So such that it will be in terms of the block upper triangular matrix. And what is the specialty of this block? So this diagonal blocks has some characterized. Here it can be anything. So these diagonal blocks is of the form D plus. What is that? That means these blocks are also permutation to a positive diagonal matrix. Fine. And at least one of them block is not. It should be more. Size should be more than 2. Okay, then this characterize the all the sign patterns that allows the minimally semi-positivity. So the next question is, what about the requires? So answer is yes. We also characterize the sign pattern which requires the minimally semi-positivity, and this result it says that the sign pattern requires the minimally semi-positivity if and only if there are permutational matrix P and Q such that PSQ has the Z form. So it means that we have seen that it means that this S is a generalized positive column. And each column of this matrix, of this new matrix, contains a frontal plus. Fine. So that is the only plus in its row. So now let us see what is that meaning. So I'll be going back here. So it means that if it is a minimally semi-positive and if it is required, So this is the frontal plus, and it says that this is the only plus on each row. So that means if it is positive, and all should be either negative or zero. Okay, so you can see that if it is, yeah. So that's what it says, that it's required the that's the characterization for the sign pattern matrix that requires the minimally semi-positive matrix. So now that's the minimally semi-positive. We are done. We are talk about the characterization of sign pattern that allows as well as that requires the minimally semi-positivity. Then the last one is the redundant semi-positive matrices, because if we are given a matrix, semi-positive matrix, it can be either a minimally semi-positive or redundant semi-positive. So definitely those properties which are for the semi-positive matrices, we expect to hold them as well here. So the first one, it says that the sign pattern is allows a redundant semi-positivity. So I'm writing it as just in the short form, RSP. If and only if each row has a positive entry, right? If you go back to the redundant semi-positivity for the semi-positive matrices, now see, semi-positive matrices, if you look at this theorem, it says that this allows semi-positivity if each row has a positive, each row contains a positive. Now here it shows that it needs more conditions that will happen for this redundant semi-positive. That will satisfy. That means each row should have a positive, and also there is a column. We can always find out a column that does not contain the only plus in any row. What do I mean? So I have each row has a positive entry. Okay, so this row is 2 rows, each has a positive entry. And the second one is, so suppose that suppose that it has a positive entry here, next has a positive entry here. Then it says that then there is a column that does not contain the only positive in any row. So I can, this is a row, so I can find out the corresponding column, and this column does not contain this. That means this column also contain some other positive entry. So if these two conditions happen, then we say that this is allows redundant semi-positive. So why this is true, one can easily see. Suppose that S allows redundant semi-positivity. So that means what is that means S allows that means E has a positive entry. Okay. So now I can choose a matrix. Let A be a because A allows a redundant semi-positivity matrix. That means I should be able to find out a matrix A which is redundant semi-positive and which has the sign pattern S, and let A be that matrix. And suppose that I'm considering another matrix B. Let B be a matrix. B be a column related submatrix of A, and B is semi-positive. The existence of such column related submatrix is coming from the definitions of the redundant semi-positivity, because minimally semi-positivity means if we delete in one column, it will be no more a semi-positive. Redundant semi-positive matrix, that means we should be able to find out at least one column related matrix which is still remain the semi-positive. Suppose B is that matrix. So we are having a, so now I'm having a matrix, entire matrix here. So this is the A. Now I'm getting a smaller matrix, and how I'm getting it? I'm just deleting one row. Suppose this is the one column, so I delete it. So that means in B, that column is not here. So then I can consider the same sign pattern. So S has a sign pattern S matrix. Then that means this matrix also related with another sign pattern matrix. So let me call it as S tilde. That's what I have written it here. So that means that column detail is submatrix that is also allows the semi-positivity. Yes, because this is a submatrix of that one, and we are having a matrix B here. It says that that is also semi-positive matrix. So it means it says that this S tilde allows the semi-positivity. Fine, because we can find out a matrix B. So if allows the semi-positivity matrix, then it says that each column, each row has a positive entry. Then again in that B, it has each row of here has a positive entry. Okay, so it means that therefore the column related S did not contain the only positive. So that means that means this is not the only positive it column have. It can have other positive entries here also. It can be here, it can be here, it could be here. So similarly, one can see the converse also. Now, next is it's about I think that's the last one I wanted to discuss. Is again this is allows. So next maybe wanted to see that is requires. Okay, so it says that sign pattern S requires redundant semi-positivity if and only if S is permutationally equivalent to a sign pattern S bar having the form G. So it means the same as I can say that S is a generalized positive column, and together with that I need another condition. It says that the in this S bar is in that stress relaxation I can find out K. Fine. So that means on the first row I can find out one element which is non-zero. Okay, so this characterizes all the sign patterns that requires the redundancy semi-positive. So that means all possible cases have been covered. Fine, and there are many papers. Most of the work has been done by you can find it on these papers is by C.R. Johnson and Stanford by this is a quite an old paper. This is a qualitative semi-positivity, and then there are four or five papers I have taken as an four paper I think. Then the next one is a sign pattern then allows the minimal semi-positivity. You can find out many results over there. I haven't mentioned it here. Then another one, characterization of minimalist semi-positivity of sign pattern matrix. So this three, and this is the first one, sign pattern of the inverse semi-positivity matrix. That is also something related to the minimalist semi-positive matrix. Okay, so that's all. Maybe I wanted to say. So any doubt or anything or any questions, any suggestion? So please go ahead. I mean, many type of works are going on this sign pattern matrices. Fine, you can go ahead and you can check. People are working sometimes with the graph theory and the sign pattern matrices, and then this is another because since we are dealing with only the semi-positivity, so that's the reason I talked about the sign pattern, which is related to the property semi-positivity. Yeah. Okay, no question, no comments.
Ma'am, will you share these slides for
Yes.
sign pattern?
Yeah, I'll do that. I'll share all my slides as I already told you that I'm still yet to do some correction. I'll do it today, and then I'll share it by sometimes tonight. I hope that will be okay. All my slides, 1, 2, 3, 4 slides, I'll share with all of you, and Michael. Once Michael will share his notes, and that also I'll be sharing with all of you.
Okay.
And
these references will be there also?
Here, yes, references are there here only because I wrote it as a footnote, so you can find it here. if you are because I'm using the tab, probably that's the reason you cannot see it properly. But here you can see that nicely. So all these things are written there. So all this 4 paper, if you go through it, then that's all about the assigned pattern.
Okay, ma'am.
Okay. Initially, also when we started with working, we are thinking that okay, let us do something on the sign pattern, and then I realized okay, almost all the work has been done. But still, we will see that if there is any possibilities where one can work, some kind of generalizations or anything.
Okay.
Okay, so all of you have my email address. If any concern with the course, then you can always email me. Fine.
Okay, ma'am. Thank you.
So okay, then that's all. That's all from today. So again, we will see tomorrow at 8 a.m. And tomorrow the lectures will be given by Michael, the first 2 lectures, and then Professor Shivakumar will start his lecture tomorrow on the 3rd session. Okay, that's all then. It's bye from for now, and then I'll see you tomorrow.
Thank you, ma'am. No, this is the